Hello everybody! It's a pleasure to present at the Digital Concrete 2020 our research on complex architecture in printed concrete. The presented study describes the cohesion pavilion that was designed and erected in 2019 to showcase the state-of-the-art of 3D concrete printing. This project was part of the celebrations of the 350-year anniversary of the University of Innsbruck and was constructed in a public square on the campus. The pavilion featured a complex, irregular segmented, doubly curved and robotically 3D printed concrete shell. Extrusion-based 3D concrete printing is increasingly finding its way into built projects in the public domain and displays the potential of the technology, such as reduced use of material, geometrical freedom, and high speed of construction. The application of 3D concrete printing in projects brings the need for customized approaches in design, structural engineering, production, and construction. For the cohesion pavilion, initial sketches and preliminary studies had been developed by architecture and technical science students during the summer term of 2018. It featured a circular geometry completely filling one of the water basins that characterize the square linking various buildings of the campus in the western part of Innsbruck. Due to budget and time constraints, the footprint of the pavilion was reduced to cover a third of the initial proposal, shifting the design from covering the entire volume of a freestanding pavilion. The design and manufacturing strategy was characterizing for the appearance and used as an architectural tool to differentiate the pavilion from other 3D concrete printing projects. A simple parametric design model permitted to implement architectural requirements and examined several constraints of 3D concrete printing processes, such as geometry, topology, weight, transport, and assembly. In the final design proposal, the structure rises westwards up to 2.7 meters towards the main wind direction. Beginning with a small cantilevering bar table at the east-facing axis, a slightly declining ramp leads to an interior where integrated seating invites to linger and relax. On the outer shell, the numbers 350 are embossed in font size of 2 meters to clearly mark the university's anniversary. The whole object resulted finally in a diameter of 6.2 meters, a footprint of approximately 22 square meters, a surface area of 88 square meters. It was divided into 29 radial sections and resulted in 47 parts in total. The uniqueness of each of the 47 parts of the structure has generated obvious challenges for the structural design. Therefore, following structural principles needed to be determined first. Each part was designed to be self-supporting and not rely on structural interaction with other parts. Extensive reinforcement had to be avoided, as its placement would have been disrupted the printing process. With one notable exception of the heavily cantilevering bar table, all parts were dimensioned so as not to exceed the concrete tensile strengths. The structural geometry design was based on the assumption that any geometrical width should be a multitude of the width of the print filament, in our case 30 mm. Efficient material use requires the application of internal structures. These structures were mostly designed in vertical and horizontal manner. This was expected to be the easiest to control printing and be less vulnerable to shrinkage due to uneven drying. An innovative reinforcement concept of woven carbon fiber reinforced polymer strands was applied during the project. Due to time constraints, this innovation was only applied to a selection of the higher parts in the outer ring. Manually embedded 6 mm conventional reinforcement bars were applied to reinforce critical sections of the other parts. Within less Then 2 weeks, 47 parts, with an average pass length of 760 meters, accumulating to a total of 36 kilometers, had been printed. At an average nozzle speed of 300 mm a second, this results in a net printing time of more than 33 hours. All elements combined a weight of 12.2 tons. Due to the wedged shape of the parts, layer heights are between 4.5 and 12 mm. This was controlled by the robotic movement speed according to the required amount of material at each point of a layer. The alignment of the extruder in reference to the slicing planes is also essential for a high-quality printing, and beyond that, this takes full advantage of the 6 degrees of freedom of industrial robots. Industry partner Baumit supported the project with the Bauminator, a harmonized 3D concrete printing system containing mortar, catalyst, and printing nozzle of 10 mm in diameter. The injection of the catalyst happens at the head of the nozzle, and the so-called activated mortar obtains its required consistency for printing. The transportation of the concrete parts of over 250 kilometers from the prefab location to the site was carried out by conventional trucks for international freight traffic. To erect the pavilion, each concrete part needed to be turned carefully by 90 degrees. Using slings through the open inner structure of the parts instead of sealed anchors allowed adjusting easy to the center of gravity and avoided visible impact on the outer shell. Correctly positioning the parts posed the next challenge. The overall geometry itself does not provide a clear point of reference, but neither do the individual parts. To minimize the risk of cumulative inaccuracies resulting in parts that do not fit, the assembly sequence was started from where part 29 meets the water retainer wall. As the geometrical accuracy of the parts was also not exactly known, 10 mm wide radial seams were designed between them. The cohesion pavilion displays several important arguments for the future development of 3D concrete printing structures in the sector of architecture and construction applications. Nevertheless, the construction accuracy and divergences in the assembly process at the building site and the precision in the production process needs to be re-evaluated. Further discussion also needs to be undertaken, as in the weeks and months after the opening several cracks have been appeared in the pavilion structure, likely caused by shrinkage differences or untimely manipulation. These effects to call for development of curing guidelines and analysis tools to prevent shrinkage cracks to occur, or at least allow them in a controlled manner. An extensive observation of the condition of the pavilion during the period of more than 1 year of exposure to wind and weather in public space will serve as an important test for the future development of building components. At the time of this presentation, the cohesion pavilion has been already disassembled, but the gained knowledge, experience and practice will definitely serve for future 3D concrete printing projects.